Hello, my name is Shahriari, and this is a lecture in a series of lectures on introductory linear algebra based on my book, Retrolinear. The subject of this lecture is exploring the relationship between solving a system of linear equations, ax equals b, and column space of a matrix. So first of all, systems of linear equations as matrix equations. If I write the equation ax equals b, where a is an m by n matrix, x is an n by 1 column vector of unknowns, and b is an m by 1 vector, what does that mean? Let's take this example, for example, where a is a 3 by 4 matrix, x is 4 by 1 vector of unknowns, and b is 3, 5, 7. What does it mean to say ax equals b? If you find ax, what you have to do is multiply the matrix by that column vector, and what you would get is a 3 by 1 column vector whose first entry is 3x minus 2y plus 5z minus 8w. And if you say that I want that to be equal to b, then what you're saying is that you want these three entries to be equal to 3, 5, and 7. So the first one to be 3, the second one to be 5, then the third one to be 7. So what you're saying is that you are trying to solve a system of linear equations, and you want to find out x, y, and z that simultaneously satisfy all three equations. So ax equals b is just another way of saying that you want to solve a system of linear equations. The matrix equation ax equals b represents a system of linear equations with coefficient matrix A, vector of unknowns x, and the right-hand side vector b, and vice versa. If you start with a system of linear equations, you can always turn it into a matrix equation. And if A is m by n matrix, then there's m equations and n unknowns, because every row of the matrix is corresponding to an equation, and every column of the matrix is corresponding to a variable. Another thing we have talked about in a previous video is thinking of matrix multiplications in terms of the columns of the matrix. If A is an m by n matrix, a matrix that has m rows and n columns, and here I've identified its columns, C1, C2 through Cn are the columns of this matrix, and there's n of them. Each one of those columns is m by 1 column vector. It has m entries. It's not just a number. Each one of those is a column vector. If I have another column vector, an n by 1 column vector, that I want to multiply A by that, so D is gamma 1, gamma 2 through gamma n, then one thing that we saw by just multiplying it using the definition of matrix multiplication, and this was done in a previous video, but it's a pretty straightforward thing, is that A times D is a linear combination of the columns of A. So when you multiply a matrix by a column vector, you will always get a linear combination of the columns of the matrix. And when you find a linear combination, you need the scalars. Where do those scalars come from? They come from the column vector. So again, one more time, when you multiply a matrix by a column vector, you get a linear combination of the columns of A, and the scalars in the linear combinations are the entries of that column vector. The final review thing, which again was in a previous video, is what's a column space of a matrix. So if you have a matrix, here is an m by n matrix, m rows, n columns, and I've identified its columns. The first column is C1, the second column C2, the last column Cn. So A is an m by n matrix, and each of its columns is an element of Rm. There's n of them, but each of them is an m tuple. So for example, if you look at the second column for a second, it's alpha 1, 2, alpha 2, 2, alpha m2. That's what C2 is, and that's an element of Rm because it's an m tuple. The column space is just the span of those. It's the set of all linear combinations of those n columns, and that will be a subspace of Rm, because the span of a set of vectors is always a subspace. So that's a subspace, means that it includes the zero vector, it's closed under addition, it's closed under scalar multiplication. The dimension of the column space is called the column rank. What does column space have to do with ax equals b? Does the column space have anything to do with solving the system ax equals b? So let's say we have A, an m by n matrix, and I've identified its columns again, C1 through Cn. X is an n by 1 column vector of unknowns, and b is the right-hand side vector, and it's m by 1. If you take A times x, m by n times an n by 1, you get an m by 1. It might be that ax equals b has a solution. It might be that it doesn't have a solution. But what does it mean to say it has a solution? It has a solution if and only if you can find a vector d that if you plug in such that A times d is b. So if you take this d and put it instead of x, And if A times D is B, then that means you found a solution. To solve this system means that there exists, that backwards E is there exists a vector D such that AD equals B. But let's unpack that a little bit. What is AD? But AD is when you multiply matrix by column vector, and we just talked about that. You get a linear combination of the columns with the scalars coming from the column vector. So you get gamma 1 C1 plus gamma 2 C2 plus gamma n Cn. So multiplying A by D is finding a linear combination of the columns. What does it mean to say AD equals B? Well, AD equals B if B is this linear combination. We have a solution for AX equals B if I can find D such that AD equals B, but that happens only if B is this linear combination of the columns. If you can write B as a linear combination of the columns, then those scalars that you use will be the D, will be the solution. So you can solve AX equals B. Again, backwards E means there exists a solution to AX equals B if and only if B is a linear combination of the column. Another way of saying that is to say that B is in the span of the columns. But what's the span of the columns? Well, that's the column space of A. What we're saying is that if a matrix walks in and a B walks in, AX equals B, and you say, well, does this have a solution or not? It will have a solution if B is in the column space of A. It will not have a solution if B is not in a column space of A. So let's write that down as a theorem. A is an m by n matrix, and B is an m by 1 column vector. X is an n by 1 column vector of unknowns. That should not be and, is n. And then AX equals B has a solution if and only if B is in a column space of A. In other words, here's the matrix A, and I might ask you, what B's can I put on the other side of this equation AX equals so that I have a solution? And the answer is exactly the elements of the column space. Or you can think of this as telling us what the column space is. The column space of A is exactly those B for which AX equals B has a solution. So we can think of this theorem also as characterizing for us column space, giving us a different way of thinking about column space. Column space is the span of the columns, but it's also all the B's for which AX equals B has a solution. The thing we just said, the column space of A is all the B where AX equals B has a solution. That works for any matrix. M and N don't have to be the same. It can be, you can have 5 equations, 37 unknowns, and it would work just as well. This result works always. But let's now think about square matrices. If we think of square matrices, n by n matrices, the number of equations is the same as the number of unknowns, then we had something called the short-long theorem, which were invertibility criteria. It was a theorem that told you that a matrix is invertible if and only if, and it gave us a whole bunch of equivalent conditions, which I will remind you in a second. And we can extend that and add to that theorem. That's a theorem that is growing as we speak. The short-long theorem was from a previous video, was that if A is an n by n matrix and X is an n by 1 column vector of unknowns, then the following statements are equivalent. And one more time, what does it mean to say the following statements are equivalent? It doesn't mean that any one of them are true or any one of them are false. What it means is that if any one of them is true, then so are all the other ones. If any one of them is false, then so are all the other ones. So there's a lot of information packed in there, because if you know any one of them, then you know all the other ones. And what are the statements? The first one is that A is invertible. The second one is that if you try to solve the homogeneous system, AX equals 0, when the right-hand side is just the column vector of zeros, the only solution is X equals 0. The fact that if A is invertible means that is pretty straightforward. If A is invertible, it has an inverse. You multiply on the left AX equals 0 by A inverse, and you get A inverse AX equals A inverse 0. A inverse 0 is 0, and A inverse AX is just X. So X will have to be 0. I showed you one direction, but I'm saying also the other direction is also true. Third one is that A is row equivalent to identity. And again, how did we prove that if the only solution to AX equals 0 is X equals 0, then A is row equivalent to identity? Well, because if you have a square matrix and you do elementary row operations, either you get an identity or you get a matrix with a row of zeros. And if you have a row of zeros and if you try to solve the homogeneous system where the right-hand side is all zeros, then you will have an infinite number of solutions because you will have 3 variables. So that was the proof from a previous video where we did this in detail, where the only solutions to X equals 0 is X equals 0 implies, not necessarily true, but if true, implies that A is row equivalent to identity. If I'm going too fast for you, definitely watch the previous video. And the fourth one was that A is a product of elementary matrices. Well, if A is row equivalent to identity, then that means that you can do elementary row operations to A and get identity. Instead of doing those elementary row operations, you can multiply A by elementary matrices and get identity. But if you can go from A to identity, you can also go from identity to A. And if you start with identity and multiply by elementary matrices and get A, then those product of elementary matrices plus identity is really just the product of elementary matrices that equals A. So A is a product of elementary matrices. And finally, to conclude the loop, we proved that 4 implies 1. If A is a product of elementary matrices, then it's invertible, and that's because elementary matrices themselves are invertible, and product of invertible matrices is invertible also. So by proving 1 implies 2, 2 implies 3, 3 implies 4, 4 implies 1, you have proved that all 4 of these statements are equivalent. If one of them is true, then all of them are true. If one of them is false, all of them are false. If A is an R by M matrix, if B is an M by N matrix, and I want to find AB, you know how to do that. You take rows of A and find the dot product with columns of B. But if you didn't want to find the whole matrix, but you wanted to find the 47th column of AB, then all you do is you take A and multiply that by the 47th column of B. And the reason for that is that the way you multiply A by 47 columns of B is to take rows of A and find the dot product with that one. And that's exactly what the 47th column of AB is. The jth column of AB is A times the jth column of B. So just remember that's a sort of a straightforward fact. So now what's a short long theorem extended? So A is an n by n matrix, X is an n by 1 column vector of unknowns, and then the following are equivalent. The following statements all are true or false. And the first 4 are exactly what I told you. So 1A is invertible, 2x equals 0 has only one solution, namely x equals 0. 3, reduced row echelon form of A is identity. That's the same as saying A is row equivalent to identity. A is a product of elementary matrices. So those are the 4 we already knew. We don't have to prove that. We proved that in the previous video. And here are the new ones. The fifth one is that if you look at AX equals B, then it always has a solution. In fact, it has a unique solution, no matter what B is. If A is invertible, AX equals B will always have a solution, and that solution will be unique. That's one thing we were going to say. The second one is that for all B in Rn, the system AX equals B has a solution. You might say, well, if it has a unique solution, of course it will have a solution. And that's true. If it has a unique solution, it will have a solution. And so if you know, for example, A is invertible, then statement 5 is definitely stronger than statement 6. You rather know statement 5 than 6, because if you know statement 5, you definitely know statement 6 also. But if you don't know A is invertible, you're trying to prove A is invertible, checking statement 6 is easier than checking statement 5 because it's a weaker statement. It says that if for all B in Rn, AX equals B has a solution, regardless of whether or not it's unique or not, you don't have to worry about uniqueness, then it will be invertible. In particular, it says that if for all B in Rn, AX equals B has a solution, that solution will be unique. Now, that's not true about any one particular matrix and so on. Like if you have one solution, you can definitely write a system where it has a solution, but that solution is not unique. But this says that if for every B, AX equals B has a solution, then for every B, that solution will be unique. Now, 7, it says for some B, the system has a unique solution. So this also follows from 5 immediately. If for all B, they have a unique solution, then certainly there's some Bs for which it will have a unique solution. But this says that if for just one B, you can find just one B where AX equals B has a unique solution, then you know that AX equals B has a unique solution for all B. By the way, one of those B's might be the 0 vector. That's part 2 that says if AX equals 0 has only one solution. But the 8th one tells us about the column space. All of these statements are equivalent to column space of A being Rn. Column space is the span of the columns. It's the subspace of Rn. This is n by n matrix. So both row space, column space, null space, all of those in Rn. The column space being all of Rn is the same as saying A is invertible. It's the same as saying A is a product of elementary matrices. It's the same as saying reduced row echelon form of A is identity. It's the same as saying for some B, the system AX equals B has a unique solution, and so on. And the 9th one, column rank, is the dimension of the column space. If you just know that that's n, then you know your matrix is invertible. And if you know your matrix is invertible, the column rank is n, and you know all these other things. So these statements are all equivalent to each other. Let's try to prove this. First of all, there's many ways to prove these equivalencies. There's no just one right way of doing it. All of them do follow exactly from any one of the other ones. And it's actually a very good exercise for you to pick two random ones like criteria 3 and criteria 5 and try to say, assume 3 and try to come up with an argument to get you to 5. And somewhere along the way, you might first prove some of the other ones. That's okay. I've just picked one way to do these. Also, truth be told, this is actually not the best way of thinking of this problem. The best way is going to come later on when we talk about linear transformations. When we talk about linear transformations, a lot of this will be put in a different light. We will look at it from a different lens, and things will make more sense. One could say that we shouldn't do any of these now. We should just talk about linear transformations, prove them in general, and then we would know all of these things. And that's true in a logical sense, not true in how you're going to learn things. Because if I just go straight to abstract linear transformations and prove things to you about kernels and image and so forth, which I will do in later videos, you will not have the intuition that will help you. And to build that, we need to prove some of these several times, and maybe not the most elegant possible ways that have been created. We will get to the elegant ways later. So I need to tell you what my strategies for proving these 9 statements are equivalent. Well, I've got 9 of these statements, 1, 2, 3, 4, 6, 5, 7, 8, 9. And I have to show you that I can go from any one of them to any other one. So if any one of them is true, then I have to prove to you that another one of them is true. How am I going to do that? Well, some of them I've already proved. For example, 1 implies 2. Well, that was a part of short-long theorem. That invertible means that Ax equals 0 has only one solution, namely x equals 0. We proved that. The second statement, that Ax equals 0 has only one solution, then that implies the reduced row echelon form of A is identity. We also proved that in the short-long theorem. We also proved that if reduced row echelon form of A is identity, then you have a product of elementary matrices. And we also proved that if you have a product of elementary matrices, then you have an invertible matrix. This was the short-long theorem that we proved in detail in a previous video. And earlier on in this video, I quickly went through the arguments. 1 implies 2, implies 3, implies 4, implies 1. But what about the rest? 5 implying 6 is obvious. If for all B, the system Ax equals B has a unique solution, well, of course, it will have, for all B, it will have some solution. If it is unique, then it has a solution. So that has nothing, there's nothing to prove. Same thing, 5 implies 7. If for all B, the system has a unique solution, then for some B, it will also have a unique solution. So there's nothing to prove there. But now we go to things that actually do need a little bit of proof. We need to prove that 6 and 8 are equivalent. So that's what I will do. That for all B in Rn, the system Ax equals B has a solution is the same as the column space of A is Rn. And in fact, the heavy lifting for this we've already done when we're talking about column space. So we have to say, why is it that if the system Ax equals B has a solution for all B, that's the same as saying that the column space is Rn. And that will not be very difficult because, as I said, we have already done the heavy lifting. The other thing we have to do is to say if the column space is Rn, why is that the same as column rank being n? One direction is obvious, the other direction is also not that hard. We will say that also. So this will show some of these things, but we need to do more. First of all, like for example, we have to be able to go from 7 back to 5 and from 6 back to 5, but I will do that indirectly. Another thing I will prove is that 1 implies 5, that if A is invertible, then the system Ax equals B has a unique solution. Among other things, it means that from any of those top row things, you can go to, if you know any of those, then you can prove 5, and from 5 you can prove 6 and 7, and from 6 you can prove these. So then that will imply that any one of those things, including invertibility, implies all of these things. But then I will also show that 7 implies 2. 7 implies 2. So you have some B, and Ax equals B. For that one particular B has a unique solution, then Ax equals 0 has only one solution, namely x equals 0. That's 2. So that will allow me from 5 to go to 7, and then from 7 go back up to 2 and go to anything in the first row. So this will allow me from 5 to go anywhere. Actually, from 5 to 2 is also an obvious thing, but I don't need to say that because I need to go from 7 up anyway. And finally, I will show you that 6 implies 1. That if the system Ax equals B has a solution, unique or not, then A is for all B, then A is invertible. And if I finish this, then you can look at this graph here, and you can see that if you know any of the statements, you follow any of, like for example, if you know 3, how do you know 8 is true? Well, you know that 3 implies 4, 4 implies 1, 1 implies 5, 5 implies 6, and 6 implies 8. So that will be true. If 9 is true, why is 7 true? Well, you go from 9 to 8 to 6 to 1 to 5 to 7. So each one of those implications will make sure that all of these statements are equivalent. Now, in each one of those, I can't assume anything, but the one thing that I'm going to assume, like if I'm going to prove 6 implies 1, the only thing I can assume, I can't assume anything about invertibility or anything else, but the only thing that I have to get to assume is that for all b, the system ax equals b has a solution, and then I have to convince you that a is invertible. Okay, so let's get started. So among the things that I said we have to prove is 6 and 8 are equivalent. If for all b in Rn, the system ax equals b has a solution, why is that the same thing as saying the column space of A is Rn? As I said, we've basically done this before. What we said is that column space of A is all the b in Rm. This was when A was m by n. In our case, so this was in general, ax equals b has a solution. So in our case, when A is n by n, the system has a solution for all b in Rn, then the column space of A is Rn. So the first statement was for general non-necessarily square matrices. That's why this is an M. But for us, we have a b is in Rn. So the system has a solution for b for all b if the column space is all of Rn, because the column space is those b that have a solution, and vice versa. If the column space is A is all of Rn, then that means that for every b in Rn, ax equals b has a solution, and we are done. Okay, so we're done with this this part of the theorem. Now let's do 8 and 9 are equivalent. Column space of A being Rn, why is that the same as saying that that the column rank of A is n? Well, the column space is a subspace of Rn, and so if and dimension of Rn is n. So if the column space of A is Rn, then that means that column space is Rn, so its dimension is n, and so that means that the column rank is n. So the column space is Rn if and only its dimension is equal to n. So if it's all of Rn, well, of course its dimension is n. But if its dimension is n, then it has to be Rn because it's sitting inside Rn. And if you have a vector space inside a bigger vector space and they have the same dimension, they've got to be the same. Why? Because you can find a basis for the small vector space, and that's a linearly independent set, and you should be able to expand that to a basis for the bigger vector space. But because but you can't add anymore because they have the same dimension, and therefore the original basis for the smaller vector space must have been a basis for the bigger one, and so the smaller one was indeed not smaller, the same size as and the same dimension as the same as the bigger one. If the two if one vector space is inside another and the dimensions are the same, then those two vector spaces are the same. Okay, so now let's try to prove that 1 implies 5. So that's only just one direction. If A is invertible, why does Ax equals B has a unique solution for all B? And this is a pretty straightforward argument that we have seen many times before. So assume A is invertible and Ax equals B, and I want to solve for X. So what do? I multiply on the left by A inverse. I get A inverse Ax equals A inverse B. I use associativity of matrix multiplication. And instead of A inverse Ax, I have A inverse A times X. A inverse A is identity. Identity times X is X. So I have X equals A inverse B. So that means that Ax inverse, if Ax equals B and A is invertible, X has to be A inverse B. That means it's unique. It can't be anything else. So, and that's the solution, A inverse B. Okay. Now let's continue, and let's try to prove that 7 implies 2. So what is it that I want to prove? That I know. What do I know? I know 7. 7 is that for some B, I don't know which B, some B is walked in, and I've been told that Ax equals B has a unique solution for that one B. But I don't know anything about other B's. Maybe it works for not, or not, but I want to show you that AX equals 0, then the homogeneous system has only one solution in that case. So assume that D is that one solution to AX equals B. B is a very specific vector. A is my n by n matrix, and X is my unknowns. And I'm assuming that D is the one solution that I was promised in AX equals B. So what does that mean? That means if I plug D in, it works. So AD is B. That's one thing I know. Now, what do I want to prove? I want to prove that AX equals 0 doesn't have any solutions other than the trivial one, other than the 0 column vector. Okay, so let's do by contradiction. Let's say it did have some other solution. So let's say that there was some H that was not the 0 vector, but and it was a solution to X equals 0. What does it mean to what it was a solution? It means that if you plug in, it works. So that means A times H is 0. So I'm assuming that A times D is B and A times H is 0. I'm trying to get a contradiction because I want to prove to you that AX equals 0 doesn't have this solution H. That's the plan. So let's see. I want a contradiction, as I said. So what I'm going to do is I'm going to plug D plus H into AX. AX was this left-hand side of system of equation, and instead of X, I'm going to put D plus H. What's D plus H? Well, D is a column vector, H is a column vector. Add them, you get a column vector. You're going to put it in. And so what do I get? I get, well, A times D plus H, not surprised. And I will use the distributive law, and I say, well, that's AD plus AH. But what's AD? AD is B. What's AH? AH is the 0 vector. So what's AD plus AH is B. So what did I get? I got that D plus H is another solution to AX equals B. And it's another solution from what? From D. D plus H can't be D, because if D plus H was D, then H would be the 0 vector, and H was not the 0 vector. So I got some other solution to AX equals B, but that wasn't the case, because that can't be the case, because the one thing I knew was that for that one B, AX equals B had only one solution, and I just found two. I had D, but now D plus H is a solution. So I have a contradiction. Contradiction to what? To assuming that AX equals Z had a solution other than 0, that H. I assumed there was an H, and now there isn't. So I proved that 7 implies 2, and there's only one thing left to do. 6 implies 1, and this is sort of a proof I like. So this is a proof that says that, let's assume the only thing we don't know anything about elementary matrices, we don't know anything about row echelon form, we don't know anything about other things or column space. The only thing we know is that for every B, AX equals B has a solution. So I have this matrix A, and if you give me your favorite B in Rn, column vector, AX equals B has a solution. And I want to prove to you that A is invertible. Okay, so and in my scheme of things, this is a linchpin. If I prove this, then the whole graph works and everything implies everything. So this is this final the thing that I need to prove. So and the proof is you wouldn't start here necessarily if you didn't know what you were doing, but it works and it's very nice. Actually, maybe you would. So AX equals B has a solution for everything. How am I going to use that? Well, I mean, the way to use that is to pick specific B and say, well, give me this answer to AX equals B. If AX equals B has a solution for all B, well, what is it for this B? And the B's that I'm going to use, maybe unsurprisingly, is the standard basis for Rn. So E1 is the column vector with 1 on top and then zeros everywhere else. E2 is 0, 1, then all zeros. E3 is 0, 0, 1, all zeros, and so forth. And En is all zeros and then a 1 at the end. So those are those. And I'm going to, one at a time, ask you to solve AX equals one of those for me. So I will say, solve AX equals E1. How do you know you can do that? Oh, well, that was our assumption. Statement 6 was that for all B in Rn, AX equals B has a solution. I don't know if it's unique or not, but it has a solution. So call the solution C1. Well, what does that mean? Well, that means that A times C1 is E1. So that means that if you take C1 and plug it in, it works. So C1 is some column vector, and A times C1 is E1. All right? Then I'm going to say, now solve AX equals E2. All right? So, and you might do that, and you might tell me that the solution to that is C2. And so that means that A times C2 is E2. So, so C2 is not the solution to AX equals E1, it's the solution to AX equals E2. And so if you plug that in, you get A times C2 is E2. And you're going to continue this, repeat this for all of them. And you will get a whole bunch of solutions. You have now got C3, so you had C1 and C2, now you have C3, C4, all the way till Cn. Each one of those is a solution to a system of linear equations. AX equals EI gives you CI. And then from those, I'm going to, and this is what I know about them. A times C3 is E3, A times C4 is E4, E times C47 is E47, and E times Cn is En. Then what I'm going to do is I'm going to make a matrix out of these. So I'm going to make this matrix C that's made up of these column vectors, C1 through Cn. What are those? Those were the solutions to AX equals B when B was E1 through En. So I found these solutions, I made a matrix of them. And then I'm going to tell you what's A times C. Well, how do you multiply A times C? Well, you take rows times columns, but when I talked about matrix multiplication early, if I want to know what the columns of AC is, all I do is multiply A by columns of C. So what I get is the first column is A times the first column of C, which is C1. So it's the first column of AC is AC1. The second column of AC is AC2 because C2 is the second column of C, and so forth. So these are the columns. But I know what these things are. AC1 is E1, AC2 is E2, and so forth. And so I get E1, E2, En. But what happens if you take these standard bases and write them next to each other? You get the identity matrix. And so I found a matrix that when you multiply A by A times C, you get identity. And so that tells us that C is A inverse, and in particular, A is invertible. So this proof was actually, the proof itself was useful because it told us how to, not only it told us that here's a fact we know that if AX equals B has a solution for all B, then A is invertible. By the way, upside down A means for all. It not only told you us that, but it told you how to find the inverse of A. And C is the A inverse of A. You solve these systems and then you have these columns and you find A inverse. By the way, AC's identity, well, does that mean CA is automatically identity? If A and C are square matrices, yes, that means that. We proved that in an earlier video. So C is A inverse and A is invertible, and the proof is complete. Again, this is a nice proof because the proof is telling us an algorithm for doing things. So if you have a matrix A and you want its inverse, and you don't really care about the inverse, you only care about the 47th column, then what do? You solve the equation AX equals E47, the 47th element in the standard basis. And the solution will be that whatever you get will be this 47th column of A inverse. Okay, so now let's recap. So we have now these invertibility criteria so far, or the way I like to say it, the short-long theorem growing, is that you have it n by n matrix. These are all about square matrices, and you have a column vector of unknowns. Then the following are equivalent. So these 9 things are equivalent. Each one of them is, if each one of them is true, then all the other ones are true. If each one of them, if any one of them is true, all the other ones is true. If any one of them is false, all the other ones are false. And so, and the nice thing about this theorem is that it's bringing different ideas together. Invertibility is about having this other matrix that you multiply, you get identity. But a whole bunch of these are about solving systems, solving AX equals 0, the homogeneous system, versus solving AX equals B. And it's telling you something about those that they are equivalent to each other. Like, for example, one of the things it's saying is that if the homogeneous system only has the trivial solution, then even if you look at the non-homogeneous system, you'll always have a unique solution also. That's not something that's so obvious right from the start. You can prove those directly. Everything here you can prove directly. But now we have proved all of these are equivalent. It also tells us that these things have something to do with column space and column rank. That one number, the column rank, is telling us if the matrix is invertible. And it's also telling us what the reduced Rothschild form of A is. It's telling us A is a product of elementary matrices. It's telling us about solving systems, what we should expect if we try to solve systems of equation. So that one number actually sort of matters, the column rank. This theorem is going to be growing, and we will be adding other things to it as well. This is the end of this lecture, and I will see you in the next lecture. Keep hydrated always.